All right, here we are. Let's take a look at this series. N equals 1 to infinity, negative 1 to the n plus 1, n squared over n squared plus 3. You notice this time we have the negative 1 to the n plus 1. So what would that mean? Well, the very first term would be positive because we'd have negative 1 squared versus if it was just negative 1 to the n, it would start off negative. So there's really the difference. Okay, the point being to apply the alternating series test, we want to identify the non-alternating part. Here it's n squared over n squared plus 3. And we'll go ahead and apply the first condition in the test. And you notice I'm just showing you the whole thing here. We want to take the limit as n approaches infinity for n squared over n plus 3. And it turns out that that's going to be infinity over infinity. So why not use a L'Hopital? Well, applying derivatives, 2n over 2n, going to cancel out nicely. And this limit will equal 1. However, the alternating series test required for this to converge, this limit needs to equal 0, and clearly it does not. So I'm going to note specifically that 1 does not equal 0. And so it seems maybe at first like we cannot apply the alternating series test because we did not get 0 like we were supposed to. Well, the alternating series test says if we get this limit to be 0, then we would move on to step 2, and if that worked out, then we would know that it converges. But it turns out if this first step does not equal 0, we can actually say that the series diverges by a different test that we learned earlier. Well, if the limit of our nth term does not equal 0, of course, the test that applies there is the divergence test. We can stop right here. It's actually, in a sense, even better news for this first step to not work out the way we're anticipating, because then we're done. Our limit of the nth term did not equal 0. That's it. It diverges by the divergence test. Now you might say, wait a second though, the AN you're talking about ignored the alternating piece, right? You didn't really take all of that when you took that limit. You only took the non-alternating part. So how can you say that the original series in its entirety diverges by the divergence test? That is a great observation. Here's why we can still say that this diverges by the divergence test. If these terms, I mean, look at it in this, for this particular case, these terms are getting closer to 1, right? These terms right here, these are getting closer to 1 as n gets bigger. Well, whether it's a negative 1 or a positive 1, it's still going to shoot off in one direction or another. And remember, it's never going to exactly equal negative 1 or positive 1. So it's not like they're just going to cancel out. But, they're getting, like a little bit, above 1 or a little bit below 1. I'm not sure, but they're getting closer to 1 way or another. So sometimes we're adding something. I think these would be getting, since our denominator is bigger, these would be getting closer to 1. They'd start below 1 and get closer to 1 the further along we went. So you're gonna be either adding something that's getting closer to 1 or subtracting something, and it's gonna still shoot off. Okay, end of the story. Hopefully that makes sense to some people out there. End of the story is we took this limit, it didn't equal 0, and we got a test for that. It diverges by the divergence test, and we are done. That's great news. Okay, I've got one more for us. And then I make this note. Oh yeah, that's nice. Just keep that in your pocket. If the first condition of the alternating series test fails, immediately we can say it diverges by the divergence test, the original series, because that is the divergence test, right? Okay, so I've got one more of these for us. How about this one? This one looks like fun, right? N equals 1 to infinity. The cosine of n pi over n squared. Oh boy. Let's see. Yeah, so it turns out alternating series test will apply here. But it does not look like an alternating series at first. We don't have a -1 to a power. So here's what we're going to do. It is alternating. It's just not clear. It's not obvious from the way we set it up, or the way it's written. But if we plug in a few values of n, then we can see how it's alternating, and we can rewrite this thing. So that's our first step here. We're going to list several terms to see how it's alternating. Okay, so in this case, if we begin with n equals 1, well, the cosine of pi is -1, right? -1 over 1. Let's see, n equals 2. Cosine of 2 pi is +1 over 4. Cosine of 3 pi back to -1. Cosine of 4 pi. Okay, so we can see it. When n is odd, we get a negative value there. When n is even, we get a positive value there, the numerator, and then we've got the denominators too. So I can see the negative, positive, negative, positive, negative, positive. All right. So now I'm going to rewrite this in a way that's clear how it's alternating. Well, the denominator is not going to change. It's still over n squared, but the numerator now. Now I can see -1, +1, -1, +1. So this is what I'm going to do. Well, if it begins negative, then I know it should be -1 to the n. So when I start it off with n equals 1, it begins as a negative. Then when it goes to n equals 2, it turns the numerator positive, and then n equals 3, n equals 4, and it all works out. So very sneaky to write as the cosine of n pi. All that is -1 to the n. I mean, because n is an integer. All right. Be on the lookout for that. Continuing from there, let's identify the non-alternating part. An here will equal the 1 over n squared. We'll get rid of the -1 to the n. And we'll apply our conditions. And at this point, really nothing out of the ordinary. It was really just the rewriting of the cosine n pi. That's the point of this problem, but let's do it anyway. First condition, limit as n goes to infinity. Well, that's clearly 0. All right. No work there. For the second piece, it'd be good to do another one of these, though, for sure. I'm either going to show algebraically that 1 over n squared is greater than or equal to 1 over n plus 1 squared, right? There's the n plus 1th term, where really the idea is I replace the n with n plus 1. So I'm either going to show this algebraically, or I'm going to show that the derivative is always negative, that it's always decreasing. Okay, so I'll just kind of do these one step at a time. I've got it kind of laid out that way. I mean, the derivative, there's really not much to say. I think this is pretty much it, actually. So if we take that derivative, well, yeah, that's a -2 over x to the third. It's always a negative over a positive, so that's always less than 0 for x greater than or equal to 1. That's a great way to show it, and you'd be done. Or you could show it algebraically. Now, what did I do here? I cross-multiplied. I took that, multiplied it by the 1. I took n squared, multiplied it by the 1, and got this. Okay, how is that helpful? I'm going to FOIL, or do I square root? Maybe I square root both sides. Yeah, let's just square root both sides. So n plus 1 greater than or equal to n. And now I can subtract n from both sides, and I'm, again, show it plainly were you just boiling it down to numbers? In most cases, subtracting the n, 1 is greater than or equal to 0. Yep, that's definitely true, so this must be true as well. And you got it. Our series converges by the alternating series test. Both the conditions are met. It's almost like that second condition is almost more challenging than the first. I kind of like the derivative in this particular case, although that's not a big deal, but it's just a little bit more writing. Okay, I want to pause here and present. We won't go through the full example, but what if you saw something like this? Cosine n equals 1 to infinity. The cosine of n minus 1 pi over n squared. What's that going to be? Again, it's not clear that that's alternating, but if you were to write out a few terms, what would happen here? Well, n equals 1, you'd have the cosine of 0, which is positive 1, and it's not until n equals 2 do you get a negative 1 in the numerator. So that little shift, now you start off with a positive and then go negative. One thing to keep your eyes open for, if you see something with a cosine n pi or cosine n minus 1 pi, obviously, or sine, right? And sine, I think, needs to use pi over 2 to get it to be a 1. So be on the lookout for those. Those are sneaky ways to present alternating series. Okay, anyway, now that we're starting with a positive, what's the series going to look like when we rewrite it? And maybe you guessed, we kind of spoken to this before. In this case, it would be negative 1 raised to the n plus 1 over n squared. And so now I'm indicating, hey, this starts positive, n equals 1, you know. Okay. That is it for our examples of using the alternating series test. There is one more concept in this section. That is for the next video.